We said there was an issue with the electric field being created solely by the battery. And so we're going to look at that in a little bit more detail. And there's this worksheet that we just handed out. If you haven't picked one up, they're at the front here, where it shows an example of a circuit with a battery. And again, we're using this kind of crude model of a battery. We're just thinking of it as two plates of a capacitor, one positively charged, one negatively charged. And then some way of maintaining that charge separation, so there's a conveyor belt driving charge from one end to the other. And then the circuit is just a single wire, but it has a bend in it. Let's see if I can kind of draw it. And something like that. Okay. All right. I didn't draw it too well, but it's meant to have the same thickness of wire for the entire circuit. Okay, so it's just a single wire, single thickness, single value of electron density and electron mobility. So here's what I want you to do. On the top part of the diagram, and in fact there may be even a question here, we can talk about this. On the top part of the diagram, just take a minute or two and draw the drift velocity of electrons in the steady state. Okay, so if we're thinking about the circuit's hooked up, it's been running for a while, we're in a steady state. Remember, a steady state means that it's not changing anymore, right? The electron velocity, or the drift velocity, is not equal to 0, so there's going to be some moving electrons. And we also know the current node rule, which says that the current in is equal to the current out, right? Current conservation, or charge conservation plus the steady state, says that current is equal to current out. And then we also know I is equal to N, A, V, and V is equal to U, E. So just reminders there. So just take a minute, draw the arrows, draw the the velocity vectors that represent the electron drift velocity at each little x on the top part of the diagram. Okay, so we've basically got this. So you should have something. Well, first of all, what's it look like? The electron. So it's location 2. Which directions are the electrons moving? They're moving toward the battery or away? They're moving away from the battery. Remember, you can think of the negative terminal of the battery as the electrons are coming from the negative terminal and moving that way, away from the negative terminal throughout the circuit. And then it kind of twists around here. And how should these arrows, what should be the relative lengths of these arrows be? They should be the same, right? Because if we're in a steady state, we have the same current everywhere, which means given the same thickness in N, we should have the same drift speed everywhere. So you should get something that looks like that, right? So I saw most of that. A couple people had the directions reversed, but we all basically had the same diagram. So on the same picture, given that in the steady state the velocity has to be this, what should the electric field be at each of those locations? So draw the electric field vectors at each little x.